This is a clock, but it's not ordinary. Making an LED clock is really easy, but soon you'll find out that you'll have a lot of issues, including faint lights, hard to distinguish characters, flicker, but worst of all, drift. Even if your clock drifts by 1 minute every day, it's going to be completely useless in a couple of weeks. So with this project, I plan to over-engineer a small pendant clock into being the perfect desk or bedside tool. Ultimately, I want this clock to prevent me from using my phone. Checking the time is almost always a gateway into you unlocking your phone and autopiloting to your favorite addictive app of choice. Whether that's the first thing when you wake up, when you're doing work, or when you're going to sleep. I also want to incorporate a countdown time into this, as well as a stopwatch. And to make this even harder for myself, I want to have no buttons, but instead one large dial to control everything. To change between the modes, I also want to be able to shake the clock. So a 7-segment display has 7 LEDs, one for each segment. Let's say we want 4 characters and some extra LEDs for other information and effects. This makes a liberal quantity of about 50 LEDs, which we want to individually control. Microcontrollers all have a limited number of outputs, called GPIOs, and so driving a crap ton of LEDs is usually not possible. Because of that, certain tricks have to be used to light up a ton of LEDs with much fewer outputs. For example, you have techniques called multiplexing or charlieplexing, where 20 LEDs could be controlled with 5 inputs. However, with charlieplexing, it's impossible to have full control of all the LEDs. Let's say you want to light up this LED. First, you disconnect this pin, connect this one here to 5 volts, and connect ground here. This causes current to flow like this, but let's say you want to light up this LED here at the same time. This would be impossible as you'd need to flip the power supply terminals while keeping the first LED lit, and these input terminals can't be stuck in quantum superposition. As another example, let's say the first LED is on, and you want to light up this one as well. Well great, that works. But now let's try to light up a third. Well, you can see that's actually not possible, as all the inputs are already being used up. So because of these issues, 99% of LED displays actually work by lighting up LEDs one at a time extremely quickly and use persistence of vision to make it look like a lot more lit up when in reality only one LED is on at any given moment. Using a technique like this though results in a lot of flicker, which can cause headaches for some people, but most importantly it looks horrendous on camera in certain lighting conditions. So if we don't want a lot of flicker, we need to find a way of keeping a ton of LEDs on at the same time. We can either use a microcontroller which has a crap ton of outputs, like this ATmega2560, or we can use another trick to multiply the number of outputs without flicker. This is a shift register, and it has multiple outputs for just a few inputs. They all work slightly differently, but generally they kind of work like this. First of all, you have a data in pin. When you set it high or low, you can see it actually does nothing. This is because there's a second pin called data advance. It's also often called clock. So while this pin is low, nothing will happen until it gets set high. When you pulse this pin, by maybe pressing down on a button, the shift register reads the value of a data pin and adds it into its internal memory, which lights up the first output. Pressing it again will shift the outputs to the right by 1, and again, and again, and so on, until it gets to the end where it gets discarded. Anyways, if we want to light up more than one light, we can alternate the data and advance pins in a certain order to get the output configuration we want. And this is what it looks like sped up. But see how all these outputs flicker whenever we want to change to a new state? Usually this is bad, and we don't want that, so this shift register has an output enable pin, which either enables or disables the output. A shift register like this is fundamentally super simple, but it requires a lot of work just to get the output you want. So all of this can be enclosed in another system that just has 2 inputs, SDA and SCL. These are digital inputs, so your microcontroller can tell it,
I want you to turn on the 1st, 4th, 7th and 8th LED.
And the chip will sort out all the shifting and enabling for you. This whole system is often referred to as a GPIO expander, and it more or less expands how many outputs your microcontroller has. These outputs are only limited to basic high or low outputs, so sending data out of these pins is extremely difficult. Because of that limitation, modern GPIO expanders have lots of bells and whistles, like being able to pass through high-speed data, having their own inputs, and also built-in analog to digital converters. Hell, some don't even use shift registers, but instead are secretly microcontrollers in and of themselves, albeit not ones you can change the code of. By the way, before you leave a comment, RGB individually addressable LEDs do exist. You know, the ones where you can have an infinite number of LEDs for just one GPIO. But I want my clock to be white. And these RGB LEDs always have a really crappy white. By comparison, this is a pure white LED. So we can connect this GPIO expander in a configuration like this into a 7-segment display, and now we are able to control every single segment to make flicker-free digits. We can then copy and paste this configuration however many times we'd like to get more digits. Because these use I2C to communicate, we can actually have an infinite number of GPIO expanders for just 2 pins on a microcontroller. Now we run into a fairly big problem, which you might not notice at first glance. This expander can only output 125 mA, so with 16 outputs being high, that's just under 8 mA per output. For reference, this LED is only drawing 20 mA, so we also need to somehow convert this low power signal into a high power one. This can be done with a simple MOSFET, which is basically a digital switch. Now our LEDs can draw however much power we'd like without any issues. We can even triple up the LEDs per GPIO, making the output much brighter. Now that we can control a bunch of LEDs with only 2 pins, we can use a small microcontroller like this, or this, or this. But instead I will use the ESP32C3 chip. This is for the simple reason that this chip can use Wi-Fi to automatically sync the time. In my design I will also use this real-time clock chip for whenever Wi-Fi isn't available. To detect the rotation of the outer dial, I want to use something like this. But we don't actually need teeth, and we can get away with using rubber O-rings for friction. By not using teeth, machining becomes a lot easier and cheaper. Then, to detect the rotation of this small inner dial, we can use a rotary encoder, which basically works by having 2 internal buttons, which alternate being pressed depending on which way you turn the knob. The final bit of hardware that we need is this small impact switch. These are mechanical devices that have an inner core with a copper spring. When there's a large impulse in acceleration, the inertia of the coil causes it to bend and make contact with the inner core. This creates an electrical path which can be detected in the same manner as a button press. There is a pretty big issue with this switch having a ton of debounce, which means the switch gets activated over and over again, but this can be filtered out in software fairly easily. Actually wait, this is easy to implement, but there are a lot of problems with an impact switch. First of all, it's mechanical and is prone to getting stuck or being inconsistent. It also only works in 2 dimensions, and you cannot adjust the acceleration threshold. So instead of an impact switch, I will be using an accelerometer instead, which solves all of these issues at the cost of, well, cost. So now that everything's figured out, we can start making the board. This is what I've designed so far. Fundamentally, it's quite simple, but I'll get into the details later. I ordered these boards from PCBWay, and as always, they are extremely high quality. I honestly can't find a single imperfection. To order your own PCBs, go to PCBWay's website through the link in my description, upload your Gerber files, and place the order. 10 2-layer PCBs that are 100 by 100mm can be ordered for as cheap as $5. So this is the design that I've gone for here. This is where the LEDs go. These pads are for the BSS138 MOSFETs, which are surprisingly cheap. This is also where a buck converter will go, to efficiently turn 5 volts into 3.3 volts. And this chip here will be the accelerometer. On the back we have more GPIO expanders, and even more MOSFETs in a ring. These control some LEDs on the edge for aesthetics. The USB port here is the main power input, the rotary encoder is here, and this will be the real-time clock. And finally here is where the microcontroller will be soldered. Alright, so enough yapping, time to get soldering. So I won't be assembling these fully. I just want to test if there are any major issues before I get this properly assembled. To do this partial assembly, I'm going to be using my own pick and place machine. Which reminds me, thank you so much for the support on the video. This project has now become my most viewed video on my channel, and I just want to thank you guys a lot for the support. Liking and subscribing is the best way for you guys to show your support, and help me keep making videos like this. I'm an independent creator, and if you've been enjoying this video so far, please consider liking and subscribing. Oh, by the way, I finally bought some new solder paste, so something like this shouldn't happen again. Once my test worked, I ordered professionally assembled PCBs from PCBWay. As you can see, these crystals here aren't soldered on. This is because I wanted to use this ESP's internal clock for non-timing critical processes such as lighting up the segments. But to prevent my clock from drifting, it'll get a 1 Hz sync pulse from this real-time clock chip. Apparently this chip is meant to be really precise, but I guess we'll find out. I am a bit skeptical as this RTC doesn't use a crystal, but remember, as a backup we do always have these pads here. In this area there are some more unpopulated components. These are all for the antenna. I have decided not to use Wi-Fi as a primary time source, as the clock will immediately break the second Wi-Fi gets disconnected. And I want this clock to be somewhat portable and not locked to my home Wi-Fi. You know what, I've really got to appreciate the assembly on these boards. God damn, this is sexy. Okay, so there's a small issue. I am missing a strapping pin on the ESP chip, which means it probably works, but it just doesn't boot. Fixing this should be fairly easy though. I just need to connect this pad to VCC. I also added this fuse and then realized that these two pins here need to be shorted together. So it looks like we aren't getting 3.3 volts at all, and there's a short between VCC and ground now? Oh my god, I'm an idiot. It's still not detecting. Turns out that I do need the crystal. Apparently that's compulsory. No worries though, I bought this crystal and it arrived a few days later. Yes, let's go, there it is. It's been recognized. I then wrote some test code. Damn, this is awesome. Installed it on a redundant UFL connector, and then wrote my final program. But you know what, I'll save it to a final reveal. Now for the body of this part, I will be using the Magmabow Z1. This is a 3-axis desktop-sized CNC machine that'll become a core addition to my home workshop type thing. I guess my workshop is just my room. Anyways, while this machine can cut foam, wood, and plastic, I want to jump straight to cutting metal. Alright, let's try to CNC my first part. This is my first time trying to use a CNC, so hopefully I don't break this. Surely nothing will go wrong if I just use the default cutting settings. It's honestly crazy how CNC machines are so affordable now. Like obviously it's not huge or industrial sized, but it can cut fairly moderately sized pieces of metal, and for being around $1,000 it's actually incredibly impressive. That's about the cost of a Prusa 3D printer. This CNC machine also has a laser attachment and can make PCBs from scratch, which I'm super excited to try out in the future. There we go, so this is my first ever part. It does have these cut marks, but if you know anything about CNC machining, you know these are pretty much unavoidable. Despite looking a little bit rough, these are actually incredibly smooth. Actually, hold on, let me sand this down real quick. Okay, wow, this is honestly insane. It's crazy how I made this at home. While waiting for the Z1 to arrive, I got a bit bored and decided to make a website. It's actually hosted right here, on my server, which I made in a previous video. I suggest checking out the tools section. It's absolutely full of incredibly useful calculators for electronics. I think the coolest part of this website is just this simple calculator here. It looks pretty boring at first glance, but the revolutionary element is the fact that you can type in SI prefixes, like milli, micro, kilo, and whatever else. This is incredibly useful as electronics pretty much always uses kilo ohms, milliamps, nanofarads, etc. So just by being able to type in these prefixes, your life becomes a billion times easier. Make sure to check it out in the description. I would love your feedback and suggestions. There are no ads, no cookies, no spam, and no BS. Just a simple website that does its job. These are plates of 6061 aluminum, and I will be carving the body of the clock from these. The Z1 also comes with a 4th axis, but I won't be using it to make this project cheaper and more accessible to anyone who wants to recreate it. Speaking of this project is fully open sourced on my printables page. If you're interested in making this project yourself, make sure to check it out in the description. The body of this clock can also be FDM 3D printed, or you can get PCBWay to make the part for you. Anyways, let's try cutting the main chassis. To To cover up this PCB, I 3D printed this diffuser. The only reason for it being so complicated is because each LED needs to have the best possible seal to prevent light from leaking between segments. These thin fences have to snake around each component just to make sure the diffuser can be pushed right up against the PCB. This did take quite a few iterations. For reference, this is what a basic thin diffuser looks like. And this is my final design. You know what, I think this project is done, so let's do a final reveal. Now, one flaw in this design is that it needs constant USB power. This clock is actually much thicker than needed because I originally wanted to have this perimeter be dedicated to a battery. I would also like to try to anodize the aluminum enclosure, or maybe even try electroplating, but maybe that'll be an idea for a future project. Since I'll be CNCing a lot more parts on my new Z1, anodizing will be the next step to achieving professional grade parts. Anyways, I hope you enjoyed the video. Please consider liking and subscribing to support my channel, and make sure to check out PCBWay, the Make Error Z1, and my website through the links in the description. Anyways, thanks again for watching, and I will see you guys next time.